Okay, so today we're going to be starting a new series where I essentially take an organic reaction, I go over its mechanism, talk about other interesting things that I want to explore about it. So within this first episode, we're going to be going over the halogenation of ketones. Now, just from this title, there may be a few terms which you recognize, one of which being halogenation. Now, halogenation is just the induction of a halogen into an organic body. So, one place where you may recognize this is within alkenes. So, alkenes have the general formula CnH2n. Say if we took ethene, this could undergo halogenation. So, ethene would be C2H4. C double bond, and that's the characteristic thing about alkenes. They have a double bond within them, and the hydrogen's drawn in. Now this could react with, say, diatomic bromine, and this would result in a dihalogenoalkane. So in this case, it'd be dibromoethane. So now it'd be C single bonded. And we have the hydrogens placed like this with bromines, one bromine on each carbon. Now, where we actually position these bromines on the carbon is irrelevant because bromine and halogens in this case are both in the same environment. So what this just means is that they readily rotate in space. And so if I drew of a different configuration, say carbon to carbon, and with a bromine up here and a bromine over here with four other hydrogens drawn in like that, it wouldn't make a difference. Now, the other thing you may recognize is ketones. So ketones, what do we know about ketones? We know they have a carboxyl group, so that's just oxygen double bonded to carbon. And the other thing that separates them from, say, aldehydes is that they have R groups coming off both sides. What that means is just that they have carbons coming off either side of this carboxyl carbon. So you could have a carbon could go on like that. So another way to denote it is just instead through the letter R. If we aren't interested in what actually occurs on this side of the side chain, we just want to know that carbons are there and there's a carbon side chain on one or both sides, on both sides of our ketone, or one side if it's an aldehyde. Now, the other thing to take note of is that within this ketone, see, we have these different carbons, but how do we actually differentiate between them? Now, there is a naming system, and the way to use it is through looking at our functional group. So in this case, it'd be the carboxyl group, and numbering each carbon that comes after the carbon on our functional group. So this is our carbon on our functional group, and this is the first carbon that comes after, and we use Greek letters to symbolize them and to number them. So the first carbon would be our alpha carbon, this would be our beta carbon, this would be our gamma carbon, delta carbon, epsilon carbon, etc. But the important thing to note as well is that on the other side, this carbon would also be our alpha carbon. But say if it only had one carbon coming off, there was no second carbon, then it wouldn't have a beta carbon, contrary to this other side. Now, the other important thing to note, and the reason that I had to mention this, is because within the halogenation of ketones, one thing to take note of is that reactions on the alpha carbon are the most reactive. So this leads to the alpha halogenation of ketones. Alpha halogenation of ketones. Now, even though we are only looking at the alpha halogenation of ketones, to keep this simple, it is important to note that polyhalogenation can occur. What this just means is that more than one hydrogen atom on our ketone can be replaced with a halogen atom. So say after our alpha halogenation occurred, another one on the same alpha carbon, another halogenation on the same alpha carbon could occur, or it could occur on a beta carbon, gamma carbon, etc. But this is less and less likely as the reactivity of ketones does decrease with each successive halogenation. So polyhalogenation is quite isn't that frequent, and our primary product, our product with the largest yield, is likely to be our alpha haloketone. However, it is also important to note that if, in the unlikely case, a trihalide ketone is formed, then carboxylates can be formed through what we know as the haloform reaction that I might cover at a later state. However, if you want to avoid this, if you want to keep it to a mono alpha haloketo product, you use an excess of ketone, and and that sort of weighs out your yield better. It's also important to note to say that if we had an asymmetrical ketone, so say for example, what's this? Say if we had that, so that would be pentan 2-one. When we say alpha halogenation, as we said before, there are 2 alpha carbons, so that means 2 isometric products can be formed. So this just means that despite having the same molecular formula, they have different structures. So what we can say is that the product mixture and the reaction itself can be stereoselective. So it's just different products, but different due to their different structural configurations. Say a hydrogen on this carbon could be replaced with a halogen. Halogens will just denote as X. So this hydrogen could be one hydrogen could be replaced by a halogen on this carbon, or a hydrogen could be replaced with a halogen on this carbon, and it'd still be the alpha halogenation of ketones, even though 2 different products are formed due to their isometric differences. So we also said the X would be the way that we denoted halogens, but most of the time halogens are diatomic, so X2 is the easiest way to denote that. So if we actually go on to the reaction itself now, covering its mechanism, it's important to note that here we are covering the acid catalyzed halogenation of ketones. The halogenation of ketones can also be base catalyzed, but that's slightly more complex, and it's going to be probably in part 2 to this video. The difference between this is that obviously because it's acid catalyzed, that means that there's going to be an input of H plus ions, and we get this from an acid. We know that when it dissociates in water, it gives out H plus ions, so we call those arrhenius acids. So if we actually wrote this out as part of the natural dissociation of water, we have H2O, reversible reaction, forms H plus and hydroxide, and our hydroxide ion OH minus. But in reality, what actually happens is that we have 2H2O forms the hydronium ion H3O plus and OH minus. This is what happens in reality, and it's going to be this hydronium ion that plays a large part and factors in to our acid catalyzed halogenation of ketones, and it actually occurs in the first step of our reaction. The first step of our reaction being the formation of an enol, and this is acid catalyzed, and the reason this is important is that our enol, unlike our ketone, can readily react with our halogen. So once this happens, we move on to step 2, where the enol and the halogen react together, and what this forms is a cation intermediate, and that leads us to step 3, where we are finally left with an alpha haloketone product, which is what we want to form from our starting ketone. Now, if we actually move on to the reaction itself, let's start with step 1, which is enol formation. So we have our ketone, which we don't really care what's on one side, so let's just call this side R, and we have the carboxyl group, so this is what makes it a ketone. We have one carbon coming off like this, and so we know that this chain continues, and it goes on and on, and it goes on and on and on, but we don't really care about that. So we can just write it as being, say, if this was R1, this would be the continuation of our carbon chain, so this could be R2. We also know that because this carbon is forming 2 bonds, so that just suggests that 2 hydrogens are remaining, so we could have, say, 1 hydrogen coming down here, 1 hydrogen going up there like that. So we know that this step is, what do we know about it? We know that it's acid catalyzed, but another important thing to know is that it is a rate determining step, so this is going to be our slow step in the reaction. So we know that it's slow. We also know it's acid catalyzed, so we'll just put H plus. We could put H3O plus, it's the same thing. So what do we know about H3O plus? Well, it's oxygen. So if we just draw oxygen, we also know that there's free hydrogens coming off it, so free hydrogens coming off it like that. So the important thing to know throughout this reaction mechanism, the halogenation of ketones, are the lone pairs on the oxygens. So we know that this has a positive charge, so we know that this oxygen has 1 lone pair, and we know that this oxygen, because it forms a double bond with this carbon here, has 2 remaining lone pairs. This is really important. And this reaction all centers around oxygen, and protonation and deprotonation. And protonation and deprotonation just means the loss and gain of hydrogen, because hydrogen is just H plus ions essentially. It's essentially the same thing as a proton, so we just call it protonation and deprotonation. So the actual first step in this reaction is where our carboxyl oxygen, its lone groups, are choose to attack the one hydrogen on our hydronium ion and deprotonates it. So what actually happens here is that it attacks this hydrogen, so this forms it to break the bond with our hydronium ion, and this leaves us with neutral water. So this hydronium ion now becomes water. However, this actually, in reality, this occurs simultaneously. This lone pair on the water chooses to attack a halogen on our alpha carbon, deprotonating it. So this bond is now broken. It returns to our alpha carbon. And so what this actually causes within our ketone, because this occurs simultaneously, is that this oxygen here forming the bond with this proton causes it to become positively charged, while this, our alpha carbon, losing its proton causes it to become negatively charged. Now the solution to this is that this carbon will form a double bond with the carboxyl carbon, and this shifts the negative charge up. It shifts electron density upwards, so that this double bond will return back to our oxygen here, leaving both our alpha carbon and our carboxyl oxygen with neutral charges. And so what this ends up leaving us with is singly bonded hydroxide to our carboxyl carbon and our R1 group that we don't really care about. And then we have here our double bond to our alpha carbon. Now it only has one hydrogen remaining, and our R2 chain. So this is step 1 of the reaction. And of course, because this hydronium both loses a hydrogen to our carboxyl oxygen, but also gains one from our alpha carbon, it stays as H3O and replenishes itself as in the form of our acid catalyst. We know that catalysts aren't used up, and this is how. So step 2, this is a fast step. And it's what happens between our enol and our diatomic halogen to form our cation intermediate. So what actually happens here, if we draw in our enol once again, we have our R1 group that we don't really care about, now singly bonded to our carboxyl carbon, and then we have OH now because this is enol, double bond, alpha carbon, hydrogen, R2 group. So this is our enol, and what we're adding to it is our diatomic halogen. So we know that it's denoted through X, and we know that they're singly bonded to one another, so we can just write it as that. And what actually happens, because we now have an enol, is that it has this double bond, and this pi bond forms a region of high electron density. So when our diatomic halogen comes into close proximity of it, it acts as a sort of nucleophile, and it causes electrons to shift from our closer halogen atom, say the one on the left, towards the one on the right, and this causes the heterolytic fission of our diatomic halogen. So this resultantly creates a halogen cation and and our halogen anion. And what this actually can cause is our double bond, our pi bond, to attack our halogen cation while breaking the diatomic bond that it has, but while doing so shifts electron density downwards on the molecule, as our alpha carbon now has to form another bond. So this oxygen here with its single lone pair now chooses to shift electron density downwards and reform a double bond with the carboxyl carbon. So this leads to our R1 group bonded to our carboxyl carbon, double bonded to our hydroxide, but this is now our oxygen is now unhappy because it's forming freight bonds. Therefore, it will have a positive charge. We have formed our cation intermediate. It's going to be single bonded to carbon, hydrogen, but now importantly, a halogen and our R2 group. The halogen is the important part. So this is our cation intermediate, and of course, we are left with our halogen anion. So now we'll move on to our final step, where everything is going to come together now. You might even be able to see how it comes together. So once again, we have our cation intermediate. So we have R1, we don't care what's on this side. Carboxyl carbon, double bonded OH, it's unhappy. Oh, I should draw them separate. OH, it's unhappy. There's no lone pairs. It now has a positive charge. And we have our alpha carbon, hydrogen, our halogen, and of course our R2 group. So now what happens is that with this remaining bromine anion, it leads to the deprotonation of our carboxyl oxygen. This oxygen is unhappy. This bromine has a solution. It acts as a nucleophile. So this bond breaks, goes back to the oxygen. The electrons are return back to the oxygen, and the electrons on the bromine anion choose to attack this hydrogen, and it leads us with what we desired this whole time, our alpha haloketone product. So this is now happy. It's reformed into the carboxyl group, and now we have our alpha carbon that now not only has hydrogen, but now has halogen and its carbon side chain, and it's also stable. Simultaneously just generates hydrogen bromide, because this was the halogen that we chose, but just as easily, because this was any halogen, it could have been hydrogen hydrochloric acid or hydrogen iodide. These are actually all acids, and as we know, they can be Arrhenius acids and dissociate back into our aqueous solution to reform hydronium ions that can reset this process back all over again. So importantly, what we have done here is we have generated our neutral alpha haloketone product from our ketone, where one hydrogen atom has been replaced with one halogen atom, and this can occur for many more times within our polyhalogenation.